Hello, everyone. This is an important lecture with an important topic in calculus, and it's known as continuity and discontinuity. We want to discuss the continuity of a function. First of all, how can we identify if a given graph is the graph of a continuous function or not? Just a simple idea. If you can draw the graph of a function without taking the pen off the paper, then that means that you are dealing with the graph of a continuous function. See, for example, I'm drawing this function right here, and without taking the pen off the paper, I could draw the graph of this function. So this is actually the graph of a continuous function. But if you're supposed to draw the graph of a function where you draw part of it, okay, and then you are obliged to take the pen off the paper and then continue from somewhere else and then complete the graph of the function, then in that case, because you take the pen off the paper, so we have to say that you are drawing the graph of a discontinuous function. Just as a short, introduction. But the theoretical definition of continuity is this. A function f of x is continuous at x equals a when all of the three conditions below are met. So three conditions must be met for you to say a function is continuous. If even one of them is not satisfied, then we say, you know what, the function is discontinuous at that point x equals a. So the first condition is that f at a must be defined. So it's like very logical that um, if that x equals a does not even belong to the domain of the function, then if the function is undefined at x equals a, then obviously it's discontinuous. So f at a must be defined to begin with. Second of all, the second condition is that the limit of f of x when x approaches a must exist. So this means that if you find your left-hand limit and right-hand limit, you should end up with the same number, because otherwise limit would not exist. So limit must exist and f at a must be defined. Condition 1, condition 2. And condition 3, it's very simple. It says that these two that we mentioned above have to be equal to each other. So limit of f of x when x approaches a should actually equal to the f at a, which is the value of the function f of x at x equals a. So these three conditions must be satisfied for us to say that the function f of x is continuous at x equals a. Otherwise, we call it a discontinuous function at x equals a. We have a piecewise defined function here. Part of it is a parabola, x squared plus 1. Part of it is a linear function with a positive slope of 1. It's rising from left to right. This quadratic definition is when x is less than -2. The linear definition is when x is greater than or equal to -2. And it says fully discuss the continuity of f of x at x equals -2. Okay, so we're going to consider the first condition. We're going to say, okay, well, what do we have here? We have a quadratic function, we have a linear function, and x can be like any number less than -2, x can be any number greater than -2, x can be -2 itself. So basically, we're going to say the domain of this function is a set of real numbers, and we can say that f at -2, -2 plays the role of lowercase a for us in this exercise. F at -2 is actually defined, and I have to plug in here -2 plus 6, and that is actually equal to 4. So we see that the first condition is satisfied. F at -2 is defined. It's equal to 4. So that is fine. The second condition, limit of f of x when x approaches a must exist. So we have to take the limit of f of x when x approaches -2. But the thing is that this is a piecewise defined function. So on the left side and right side of -2, we have two different definitions, obviously. So this means that I need to find the left-hand limit of f of x when x approaches -2 from left side, and I have to find the limit of f of x when x approaches -2 from right side. Okay, and I'm crossing my fingers hoping that these two limits will equal to each other. Okay, so this would be limit of, because x approaches -2 from left hand side, so I'm using the first definition, x squared plus 1. And when you do the direct substitution method, you end up with 4 plus 1, which is 5. So this is the left-hand limit. And when x approaches -2 from right side, I'm using the other definition, the linear function x plus 6, and if x approaches -2, this time the answer is clearly 4. So we saw that the left hand limit was 5, but the right hand limit was 4. So we're going to say since left hand limit is not equal to right hand limit, thus we're going to say limit of f of x when x approaches -2 does not exist. And this means that the second condition is not satisfied right there, okay? Because in order for the function to be continuous at x equals -2, it had to have the limit actually. But we see that limit of f of x when x approaches -2 doesn't exist. So despite the fact that the first condition is satisfied, the second is not satisfied, therefore it's not continuous. So conclusion is that we're going to say f of x is discontinuous at x equals -2. That's our conclusion. Is this function continuous? No, it is not continuous. The third condition, we don't even bother checking it, okay? Just to show you a visual, this is the graph of this piecewise defined function. We have the parabola y equals x squared plus 1. We have the linear function, the straight line y equals x plus 6. But the other part, this part that you see, I did draw it with dashed lines, should not be taken into account as part of the graph of the piecewise defined function, because the parabola is the definition of the function only when x is less than -2. So if x is less than -2, sure, we are moving along a curved path, a curved parabola. But if x is greater than -2, then we have this straight line rising from left to right. And if x is exactly equal to -2, the definition says that f at -2 is actually 4. So that means a solid dot on the line, but an empty circle or a hole on the parabola, basically. So you see that there is an obvious gap there. If I enlarge this part when x is -2, you see that we have a solid dot on the line y equals x plus 6, and we have an empty circle or a hole on the parabola, okay? Why is it this way? It comes from the definition. Because when x is -2, then f at -2 is -2 plus 6, which is 4. It is not like 5. Therefore, I cannot draw a solid dot on the parabola, but I have to draw the solid dot on the line actually. And you clearly see that there is a gap, and that actually confirms that the result that we derived analytically, and analytically we said that the function is discontinuous at x equals -2. Actually, it is confirmed and verified by the graph as well. Okay. Now, how many types of discontinuity do we have out there? Well, this is one scenario that happens, and actually this is called a jump discontinuity. And jump discontinuity is whenever there is a break or there's a gap in the graph, and the limit of f of x when x approaches c, let's say, from left side is not equal to the limit of f of x when x approaches c from right hand side. Basically, the limit doesn't exist. So the second condition of the continuity is not satisfied. This is when we'll always have a gap or a break or so this sort of jump in the graph, and we call this jump discontinuity. So the type of discontinuity we just discussed here, we said f of x is discontinuous at x equals -2. If they say what is the type of the discontinuity, we're going to say this is a jump discontinuity. Okay, that is when there's a gap or break in the graph as a result of the second condition not being satisfied. And sometimes we have a vertical asymptote, like in rational functions, for example, and the graph approaches positive infinity on the left-hand side, and then on the right-hand side it approaches negative infinity. So limit of f of x when x approaches c is either positive infinity or negative infinity. It basically doesn't exist, okay? So once again, the second condition is not satisfied, but for a different reason. Not for the reason that left-hand limit is not equal to right-hand limit, but for the reason that the graph actually approaches infinity when x approaches c. And this type of discontinuity is called infinite discontinuity. So jump discontinuity and infinite discontinuity. Okay. Sometimes we have the graph of a function with only a single hole in it. Okay. The reason why there's a hole, because this function was not defined at C. So f at C is undefined. In other words, the first condition is not satisfied this time. And if this happens, well, you can easily remove this discontinuity by just putting a solid dot on the empty circle and filling in the hole, basically. And that's the reason why this type of discontinuity is called removable discontinuity. Okay? So a removable discontinuity is when the first condition is not satisfied, f at c is undefined, there's a hole in the graph, you cannot draw the graph of the function without taking the pen off the paper. You're obliged to take the pen off the paper at this hole and then continue with the rest. Jump discontinuity, infinite discontinuity, and removable discontinuity. There's another one here where, again, we have the same hole as we said before, but it's not like f at c is not defined. It is actually defined. F at c is equal to that value of that y coordinate of that point over there. So there is a solid dot exactly on top of the hole, which shows that at c the function was defined, and it was that point right there. But limit of x when x approaches c, which itself does exist by the way, is not equal to f at c. So right now, if I find the limit of this function when x approaches c, I would say it's something like -2, -3, something like that. Okay, but f at c is above the x-axis, like 1. So if f at c is 1, and then the limit of the function when x approaches c is like -3, these two are not matching, which means that the third condition is not satisfied. So whenever the third condition is not satisfied, we call this type of discontinuity a point discontinuity. Okay, so there's 4 different types of discontinuities out there. You need to know the names: jump discontinuity, infinite discontinuity, removable discontinuity, and point discontinuity. In some textbooks, point discontinuity and removable are taken as the same. Okay, but when you think about it, they're not the same. Okay, because removable discontinuity is when the first condition is not satisfied. This one, the point discontinuity, is when the third condition is not satisfied. Here, f at c is undefined. The function is not even defined at s equals c, but here it is actually defined, and that point is actually part of the graph of the function. But the third condition is not satisfied, meaning that limit of f of x when x approaches c, which of course exists, happens not to be equal to f at c, which is the value of the function at x equals c. And that's what we call this point discontinuity. There's an exercise here. It says find the real constant k such that f of x, this piecewise defined function, is continuous for all x. Okay? When we say it's continuous, it means that all 3 conditions are satisfied, no questions asked. So I can easily say that f at 4 should equal to limit of f of x when x approaches 4. So because I do know that the function is supposed to be continuous, so I do know that f at a must be defined. I do know that f at 4 is defined. I do know that limit of f of x when x approaches 4 does exist. And furthermore, I know that these two values are actually equal to one another. And I know all of these. Why? Because it is given. It is not required like before. Here we have to show that the function is continuous or discontinuous. But here it is given that it's continuous. So if it is continuous, well, no brainer, all 3 conditions must be satisfied, and they are actually satisfied. And that's the reason why I can write this. I can say f at 4 is equal to limit of f of x when x approaches 4. Now f at 4 is going to be k, because the piecewise defined function tells us that f of x is equal to k if x is 4, and if x is not 4, then we have that fraction. So here, the limit of that fraction or rational function when x approaches 4 should equal to k. Now, to find this limit on the right-hand side, obviously, direct substitution method doesn't work because it gives us the indeterminate form of 0 over 0. Therefore, we're going to use the technique of factoring. We're going to factor the numerator using difference of squares. We're going to factor the denominator. And after simplifying the right-hand side, and x minus 4 cancel out each other, so we get x plus 4 on the right side. And limit of x plus 4 when x approaches 4 by direct substitution method is 8 actually. Okay, and there you go. From there, we say k has to be 8. So the value of k, which was the puzzle, we didn't know what k is. Now we do know that k must be equal to 8. If k equals 8, then this piecewise defined function f of x will be continuous for all x everywhere, and no questions asked. Okay? All right, so I hope you understood about this topic of continuity and the three important conditions. I give you one example. We saw what happened to the graph. Four types of discontinuity was discussed, and we even did another exercise. Now you have to keep practicing and do so many different questions from your textbook, from anywhere you can find, and see how these continuity problems are generally dealt with. Thank you.